Here's another video of the lecture Intro PDE. In this video we present section 3.3. We present the whole section 3.3. The section is called Maximum Principle. Okay, we start with the strong maximum principle. Let's first read the statement. If a harmonic function u has on a path-connected open domain a maximum, then u is constant. Okay, let's look at the proof. Yeah, let a harmonic function u take at the point x of an open path-connected domain a maximum. Yeah, so x is the maximum. Yeah, then u of x minus u of epsilon is always non-negative. So we get by the mean value property, this integral is clearly this integral. Yeah, and here we integrate over y. So since this doesn't depend on y, yeah, this is the difference of u of x minus the mean, and so this is 0. Yeah, so this is 0. And if this integral, u is of course a continuous function since it's harmonic, so it's twice differentiable and then it's continuous. So it's a continuous function and this vanishes, the integral vanishes. Yeah, so the maximum is taken on this ball, on the whole ball. Yeah, on every ball which is completely contained in this set. So we have here some set omega, path connected. Yeah. Okay, let's assume. We have here, then we connect x, and now we choose two arbitrary points, x and y. And then we may choose balls around this points, yeah, which intersect. And every point in this path is contained in such a ball. So we may cover the path by finitely many such balls. And then we know on the first ball, yeah, or here on this ball, it's constant equal to the maximum. Then it's also on the next ball and so on. And by this we obtain the maximum is also taken at y. So, and since this is true for all x and y, and since it's path connected, every 2 points are connected by such a path, so u is really constant. This proves the strong maximum principle. Now the weak maximum principle. The weak maximum principle is a direct consequence of the strong maximum principle. Let a harmonic function on a bounded open domain extend continuously to the boundary. So we have here omega. Also this is strong maximum principle. And now we explain the weak maximum principle. Yeah, here we do not assume that it's bounded. Yeah, it might be arbitrary far away the y, but any x and y is connected by some finite path, so the argument applies to any pairs. Here it's bounded. This is bounded. And then we have the boundary. And omega, this is compact. Okay, and we assume that we have a solution, a harmonic function, which continuously extends to the boundary. Then the maximum is taken on the boundary. Yeah, so omega, the closure is compact, and since the closure is compact, the continuous function has a maximum. Yeah, u has a maximum. Now, if the maximum is not taken at the boundary, yeah, then it's taken inside. And then on the path connected component, so in this situation, there might exist several components, but then it's only constant on the connected component which contains the maximum. But this component clearly has a boundary. So it's constant and on the whole set, and so the maximum is also taken on the boundary and of this component, and so we really obtain the conclusion. So it's a direct consequence of the strong maximum principle. Now we come to, I think it's the only place in this lecture where we consider more general elliptic equations. Yeah? Here, now we really consider a more general elliptic equation of this form. Yeah? And we assume here on an open domain we have such a differential operator. Yeah, here this is a matrix, so it's a linear operator, and we assume if this matrix of second derivatives, that this is really as a symmetric form is positive definite. Yeah? This is what we assume. Yeah? Okay, we explained this in chapter 2. We may, without loss of generality, we may assume that this matrix is symmetric. Now we have the following theorem, yeah, which is the only statement about more general elliptic theories. So we want to explain a little bit, give you a rough impression how elliptic theory can be extended, yeah, to more general situations. Okay, so let elliptic and the coefficients should extend continuously and elliptic to the boundary. Then every twice differentiable solution of this equation, which extends continuously to the boundary, takes its maximum on the boundary. Okay, so this means we now prove the maximum principle for such elliptic theories. As a first, we show that we have some uniform ellipticity, so that there exists a lambda such that this is true not only for all k, but also for all x in omega. Yeah? And this just follows by continuity, yeah? Because we take this continuous function on the closure of omega, which is compact, and the n-1 dimensional sphere, so the boundary of the unique ball in Rn. So k are unique vectors. Yeah? And then since this is clearly quadratic with respect to k, we may normalize k. Yeah? Okay. And then this function here, this continuous function, has a minimum, so L is uniform elliptic. Yeah? So we have such a constant lambda here. Yeah, this is bounded below by some constant lambda times k square. Yeah, so this implies that sum aj 1 to n aj of chi I, chi j is larger or equal to lambda k square. Yeah, for all x in omega, in the closure of omega, and all k in Rn. Okay, and this we mean by uniform elliptic. And now we introduce a function v. This is clearly positive. Alpha should be also positive. Now if we calculate the derivative, we get only first, it depends only on x1. Yeah, so we only get, if we take the derivatives, only this contributes, and here an alpha, square plus this, Okay, and since this is larger than this, and since B is bounded, we since I are bounded on the compact sets, therefore there exists an alpha. If we make alpha very large, then this is larger than this. Yeah, this can be negative, but it's bounded. So if we make alpha large enough, then it's positive. Yeah, then we have that this function is positive. Okay, by linearity, yeah, we have L of u plus epsilon v. This is of course L of u plus epsilon LV. And this is larger or equal, since this is non-negative, epsilon LV, and this is positive. Okay, so this is positive, and for all epsilon. So the continuous function clearly attains on this compact set a maximum. Yeah, so the first derivative, yeah, the first of the function vanishes at the maximum. So this gives no contribution at the maximum, and the Hessian is negative semi-definite. Yeah? At the maximum, the Hessian is negative semi-definite. Yeah? And if one has a semi-negative symmetric matrix, we may always write this with so non-positive numbers and diagonalize it. So we may write this in this form here. Yeah. So this matrix B are just the we diagonalize it. Yeah. So by an orthogonal matrix. Yeah. Since for a symmetric matrix the eigenvalues are orthogonal, so we may diagonalize it by an orthogonal matrix. Okay, so we obtain this formula. Now by the ellipticity, yeah, we have that minus this here, the minus Lu plus epsilon v of x0 is large. Okay, the eigenvalues, these are non-positive. Yeah, the lambda i's are non-positive. Now let's calculate. Minus L of u plus epsilon of v at the maximum 0. We take a minus because the second derivative is non-positive. So this is just j ij over x0 with a minus, yeah, and then we obtain this matrix. So also over k, so we have b k I lambda k b k j. Okay, and so minus the lambda k's, this is clearly non-negative, so it's positive. Yeah. So and now we may apply ellipticity. Yeah. So this minus we put here. So and now we first take the sum. We put the sum over the k outside k. Then we have minus lambda k and sum over ij, and then we have iaj b k I b k j. Okay, and this is exactly of this form here. And now we may use this. So this is larger or equal sum over k lambda k, and here we just should take here the norm. So this means we should here take bk sum over I, bk I square, and minus, sorry, and lambda, and a minus. Okay, and so this means this is larger or equal to 0. Yeah? This is clearly larger or equal to 0. Okay, and this contradicts to that L of u plus epsilon v is larger than 0. The negative is, so the negative is larger or equal to 0, so this contradicts here too. Therefore, xi has to belong to the boundary for all epsilon larger than 0. Okay, and now this means that the supremum of u of x on the boundary, and now we add epsilon times the infimum of v of x on the boundary, on the whole set. V is clearly a positive function, so this is something positive. This is clearly smaller or equal to the supremum x on omega of u plus epsilon v of x. Because if we take here the points where it's very large and add the smallest one, then we are of course smaller than the corresponding value here. So if we take here the supremum, then this is clearly larger or equal to this one. And by our considerations, this is exactly the maximum on the boundary of u of x plus epsilon of v of x, and this is clearly smaller than the maximum of u of x on the boundary plus epsilon mal the maximum of v of x on the boundary. Okay, now since this is bounded, and since this is bounded in the limit for epsilon going to 0, we obtain supremum of u of x in omega is of course smaller or equal to the maximum x in omega plus epsilon of the maximum of v of x at the things minus infimum v of x in omega. These are two numbers. Of course, these are positive numbers, but these are bounded. So in the limit epsilon, we obtain here that this goes to 0, so we obtain maximum x. So we have proven the weak maximum principle for general elliptic equations. Okay, so this is what we want to do today. let's recall what we have done. Yeah, we had a simple consequence of the mean value problem, namely the strong maximum principle. Then we derived the weak maximum principle, and then we gave another proof for general elliptic equations for the weak maximum principle. Thank you.